Hey everybody, welcome to another installment of Calculus. Yay! I don't know what else to call it, but this is section 4.1, extreme, extrema, maxima, and minima. But we're really going to be focusing on what's known as the absolute or global. We'll call them absolute maximums and maxima and minima for functions. And so the absolute maximum is the largest that your function ever gets, and your absolute minimum is the smallest that your function ever gets. You'll see right now that I have your textbook open, and I will refer to a few things in your textbook that you can access through MyMathLab. And so the definition of absolute max or min is given right here. So you're an absolute maximum if you are always greater than or equal to every single y value, and you are an absolute minimum if you are always less than or equal to every single y value. And so it's a pretty simple concept. If you take a look, for example, in this function here, this is the graph of x squared. As you know, these sides here, the parabolas, it goes on forever, right? And so on the interval of interest of negative infinity to infinity, the entire domain is there's no absolute maximum because it goes on forever, but there is an absolute minimum of 0 because when x equals 0, y equals 0, and that is the very lowest point on the graph, that is the very smallest value of y that your function x squared ever attains. It's always greater than or equal to 0. So if we said, okay, instead of looking at the entire graph of x squared, let's just look at part of the graph. We're going to look at the graph from 0 to 2, starting at 0 and ending at 2, and including those endpoints, then you'll notice that there is now an absolute maximum. The absolute maximum happens on the right endpoint here as x goes to 2, y goes to 4, and you actually get there. All right, we're not talking limits now. We are talking about you actually have to arrive to be a maximum. You have to be a function value. It's not just approaching it. So what that means is there's an absolute maximum when x equals 2 and an absolute minimum when x equals 0. If I were to go to the open interval, though, 0 to 2, there aren't any absolute maxes or mins at all because you get all the numbers up to 4, but you don't get 4. You get all the numbers down to 0, but you don't get 0, right? What's the smallest number before you get to 0? There isn't one, right? 0.1, 0.01, 0.0000001, and you could just put more O's in there. You're still positive, you're still bigger than 0, you're still on your graph, but there's no smallest number there. So you can tell that the function obviously has something to do with this, but the interval of interest also has something to do with this. So when we are talking about absolute maxes and mins, we're going to be talking about when you really are guaranteed to have one. And so the extreme value theorem, sometimes called the EVT for short, the extreme value theorem says this, that if your function is continuous on a closed interval, continuous obviously is important, then it has an absolute maximum value and an absolute minimum value on that interval. So there's 3 parts to this that you've got to have. The function is continuous, that's one part. And then the other part is that you have a closed interval, a to b. All right, and so you've got to have both endpoints involved and included in order to guarantee that you have an absolute maximum or an absolute minimum for your function on your interval. Now again, you might have it sometimes, but to guarantee it for the extreme value theorem to apply, which guarantees that you have an absolute max and min, you've got to have these things. You've got to have a continuous function, and you've got to have a closed interval that's bounded by a and b, some real numbers. Okay, so we're going to go down here to, now that we've kind of talked about how to do that, we're going to go down here and talk about how you actually do calculate the extreme values. All right, if you go back and look at this picture right here, notice where the extreme values are. There's an extreme value here at a, x equal a, that's an absolute max. But then at b, that's not the minimum at all, right? Where's the minimum happen? The minimum happens at c, right? That's the smallest point right there at c. Now, what do you notice is going on there? Well, that's a place where the function stops decreasing and starts increasing. And as we talked about in section 4.3, increasing, decreasing is given by what? The first derivative. And when do we change from increasing to decreasing? When we have a local max or min, that's when the first derivative either equals 0 or doesn't exist, and we call those critical numbers. And so the process for locating your absolute maxes and mins starts with the same process we use for increasing, decreasing, which is take the first derivative and set it equal to 0, or if it doesn't exist somewhere, you got to include that point, all right? And those points are the candidates for absolute maxes and mins. But you could also have them at the endpoints, okay? So I'm going to switch now to the whiteboard, and I'm going to do an example problem for you. I'm going to do this first example here, part A, f of x is equal to x to the fourth minus 2x cubed on the interval -2 to 2. I'm going to go ahead and do that one for you, okay? So we have, we're in section 4.1, Extreme Value Theorem, and the first example is find the absolute max and min of f of x equal to x to the fourth minus 2x cubed on the interval. I've got to give you an interval, remember that, and let me go back and double check and make sure I get this in the right place. That's not where I'm looking. There we go. X to the fourth minus 2x cubed on the interval -2 to 2. All right, so we've got to have our closed interval there. We include the endpoints, -2 to 2. All right, so here's our example, but this is going to be the process, and this is the process that we use for all 4.1 problems but not in 4.3. So we use it for all of the extreme value problems, but we do not use it for our relative extrema. That's a different process, okay? So what's the process? Step one. Step one is we need to find critical numbers. And of course, those are found by finding the first derivative. Okay, so step one is to find the critical numbers. F prime of x, in this case, I'm going to do this. I'm going to write the problem itself in a different color so that you guys can kind of delineate the example, which is this part that's going to be in blue from the basic stuff. So we find f prime of x, take the derivative. That's pretty simple to do. We get 4x cubed minus 3 times 2 is 6x squared. Okay, simple enough. And then we want to find the critical numbers, so we set that equal to 0. There's a common factor of 2x squared that we're going to pull out here and be left with 2x minus 3. And so if we set these equal to 0 individually, because we're already factored, we get 2x squared equals 0 and 2x minus 3 equals 0. So x equals 0, divide both sides by 2 and square root it. Both sides by, add 3 to both sides and divide by 2 and you get 3 halves, okay? So here's our critical numbers. We have 2 critical numbers that we need to check. Maybe we need to check them. Why maybe? Because if you remember, we are now operating on a closed interval. We're now operating on the interval from -2 to 2. And so if I get a critical number that's not inside this interval, I don't care about it, because as far as I'm concerned, I'm just looking at the function f of x equal x to the fourth minus 2x cubed. I'm only looking at that from -2 to 2. That's all I care about. Okay? So if I get a critical number of 7, I don't care about it for this interval. Well, it turns out that both of these critical numbers are involved, and both are between -2 and 2. Okay, both are in -2 to 2, and so we are good with both of them. Okay, so step one is to find the critical numbers. All right, step two, though, step two is the different part. Step two is where we do what's known as we do a table of values or some places call it a candidates test. Candidates test. What does that mean? Well, what is a candidate? A candidate is somebody who is running for office or somebody that is possibly going to fit what we're looking for. That's a candidate. And so candidates test means we have candidates for our absolute maxes and mins, and there's only two of them. The candidates are either critical numbers, those are candidates, and then also endpoints are also candidates. If you remember our pictures from earlier, those are the only real possible places that you can get an absolute maximum or minimum. So what we do is simply test each of these points. We're going to take f, oops, I'm going to do this in blue, right? So this is the actual problem. This is how I would do it. Okay, I'm going to take f at -2. I'm going to take f at +2. I'm also going to do f at 0 and f at 3/2. I want to test all of these points. If I plug -2 in here, okay, you've got calculators, so use them to your advantage. -2 to the 4th power. Make sure that you've got them in parentheses, -2 to the 4th power. -2 being inside parentheses. -2 times -2 to the 3rd power, again in parentheses, and you end up with the value of 32. If you plug in +2, you get 2 to the 4th minus 2 times 2 to the 3rd. If you plug this into your calculator, you end up with 0. Okay. If you plug 0 in, now notice where I'm plugging these in, guys. I'm not plugging them in the derivative. I'm not looking at a sign chart. I am actually plugging these into the original function. Why? Because I'm trying to determine the absolute largest value for f. And if I want to find the largest value for f, and I know it has to happen at one of these 4 points, just plug them in. There's no need to get fancy. There's no need to do anything else. Just plug in the numbers, and guess what? The biggest number is it. That's it. That's all I need. Okay, so that's why we're doing it this way. And so you plug in 0, you get 0 to the 4th minus 2 times 0 cubed. That's also 0. All right, and then when we plug in 3/2, not something I'm going to really want to have to do without a calculator, but luckily I don't have to. 3/2 to the 4th minus 2 times 3/2 to the 3rd. All right, when I go to do that, I get 3/2 raised to the 4th power minus 2 times 3/2 raised to the 3rd power, and I get negative 1.6875 on my calculator. If I change that to my fractions, I get negative 27/16, so I have an exact answer there. Okay, so which of these 4 is the largest value? That guy's the largest value. 32 is the largest value, so that's my max. Which one's the smallest? This one's negative, it's the min. And so my absolute max is 32, and that occurs at x equal -2. And the absolute min value, the minimum value, is negative 27/16, and that happens at x equals 3/2. So it's important to tell me where it happens, and important to tell me what the actual value is. But you've already found all that stuff by now. Okay, and so that's the way that you do that. If you go back and take a look at our problem again, right? Here's problem A. Here's exactly how they did it. You can read it here on the page, and you can look through and check and make sure that I actually have the correct answer. They do one better, and they give you the picture here. And so you can see here's your graph of x to the 4th minus 2x cubed, only looking between -2 and 2, right? They limited the values, this keeps going forever, right? But we don't care about that because we stop at -2. This guy comes down and then pops back up and would keep going up forever. And we don't care about that because we're only looking at our graph from -2 to 2. Okay? So there's a second example right here. B, they do an exact same example for you, x to the 2/3 times 2 minus x. And they work that out for you. Notice that you get a critical number of 0 because you have an x in the bottom, and so you have to take that into consideration because it is a critical number because that's where g prime is undefined. So that does count. Okay, so let's pull up your worksheet. This worksheet you can download from the course worksheets area in D2L, and we're going to play around with a problem here. We're going to do problem number 2. So problem number 2 is 8x cubed plus 81x squared minus 42x minus 8 on the interval -4 to 2. All right, so let's get me a new page here, and we're going to do an example again. I'll do everything in blue this time. Example 2 is problem number 2 from the worksheet, and your function is given. I got to go back and take a peek again. All right, it is 8x to the 3rd plus 81x squared minus 42x minus 8. So 8x to the 3rd plus 81x squared minus 42x, and I forgot the constant, not that it makes a whole lot of difference yet, but it will. 42x minus 8. Excellent. Okay, so keeping up with me, I'll be done here in just a minute, guys. So what's the first step? Take the derivative. Oh, sorry, on the interval, right? -4 to 2. That's important. So take the derivative. We get 24x squared plus 162x minus 42. Those are horrific numbers to try to factor, but there's got to be a common factor here between all these numbers somewhere. All right, and it turns out that 6, all right, I wouldn't expect you to know this off the top of your head, but 6 does go into all of these, and so if you factor out a 6, you get 4x squared plus 27x minus 7, and then if you do the AC method of factoring, 4 times 7 is 28, and factors of 28 that differ by 27 are 28 and 1. And so this is a little bit of maybe factoring help here for you if you don't remember how to do this. 27x comes from 28x minus 1x, and then we can factor by grouping. The 6 is still out front. We factor this 4x squared plus 28x, and then we subtract x plus 7. Remember, if you take the negative out front, it becomes a plus. Here I've got a 4x and a 4x in there, and so I can factor those out. Take out the 4x, x plus 7 minus 1x plus 7, and so you end up with 6 times 4x minus 1 times x plus 7. Okay, so getting from here to here, some of you guys don't need these extra steps, and that's fine. But remember, this is calculus, and you have to be able to do algebra to survive calculus. And so we need to be able to handle that, whether it takes you a long time or a short time. So set each of these equal to 0 and solve for x. And when you do that, you will get x equals 1/4 and x equals 7. Now, once again, we haven't done this before, but because we are going to do the candidates test only checks candidates that count. All right, and what candidates count? Candidates that are inside of our interval. That's why I picked problem number 2. Our interval is from -4 to 2. Our candidates are both 1/4 and -7. I've missed a negative sign here. Right, if you subtract 7 from both sides, you get -7. Well, -7 certainly is not in our interval, so while I want you to find this, I also do not want you to test it. I want you to dump it, get rid of it. All right, and so now to find our values, we're going to come down here. We're going to test f of -4, and we're going to test f of 1/4. I'm going to get a little longer here on the page, and we're going to test f of +2 because those are our functions. Okay, so those are our points of interest that are inside -4 to 2. There are candidates. They're either the endpoints. -4 and 2 will always test the endpoints, and then if you have critical numbers that fall inside, in between those two, you got those two. All right, so we got this big function here. I'm going to try to make this a little bit easier to follow what I'm doing. Let's select this guy here. Let's cut it, copy it, and take it to the bottom so I can see what I'm doing without jumping back and forth all the time. We'll put it right here. All right, so that's just a reminder of what my function looks like. Okay, that's f of x. Yeah, there we go. This is f of x. Okay, to come help us down here. So we get 8 times -4 cubed plus 81 times -4 squared minus 42 times -4 plus 8. Again, you've got calculators, so certainly take use of the fact that you've got a calculator and make sure that you're plugging them in correctly using parentheses as your friends. You can always have more parentheses than you need, but boy, if you miss a parentheses, you're going to be in trouble, especially with some of these big calculations that we're doing. And then plus 8, and so you end up with minus 660. That's seriously large. Plug in 1/4, large negatively, I should say. Plug in 1/4 everywhere. Okay, and again, you guys should be doing this at home, practicing as I'm doing this, taking good notes, and working through these with me instead of just watching. Just watching the video won't do you a whole lot of good. You got to participate with the video, and so hopefully you guys are doing that. 8 times 1/4 cubed plus 81 times 1/4 squared minus 42 times 1/4 plus 8, and that'll give you 2.6875. Again, if I want to try to just get my head around that, I'm fine with that as long as you don't round it off, so 2.6875. If you wanted to try to make sure that you understood the value here as a fraction, multiply or change it to a fraction in your calculator and you get 43/16. And then we're going to plug in 2 everywhere. All right, so you guys should be pretty comfortable with this by now. We get 8 times 2 cubed plus 81 times 2 squared minus 42 times 2 plus 8, and you end up with 312. Okay, so what do you know then here about these values? Your absolute maximum, it's got to be one of these three. So your absolute max is 312 at x equal 2, and your absolute min is -660 at x equal -4. It turns out this time that the critical number was not either the max or the min. That's okay. Sometimes it just happens on the endpoints, right? And if we go real quickly and pull up a Desmos page, all right, we can take a look at the graph and confirm exactly what we just saw. All right, so we're going to confirm this. We're going to type in our function y equals 8x to the third plus 81x to the second minus 42x plus 8, and obviously we're going to have to really change our axes here. I'm going to make my x-axis go from -4 to 2 because that is what I wanted. That was my endpoints, right? But then these guys have got to be really big. So I'm going to go down to negative 700 based on what we've already found as our values, right? And you go up to positive 400, okay? And so if you take a look here at your function, something goofy is going on. So this is why we test ourselves. This says -4 when you plug it in is actually 960, which is even more than the other one. So I'm not sure what happened here. Let's take a look. Did I plug my numbers in wrong, or did I graph the wrong function? 8x cubed plus 81x squared minus 42x plus 8. That's what it looks like to me. And so let's take a look and see what happens here. When I plug in 8 times -4 to the third plus 81 times -4 squared minus 42 times -4 plus 8, I get 960. This number is totally wrong. I'm not sure where that came from. And so this is a good reason to graph things out just to double check, right? You can't use the graph to be your only answer, but it certainly helps. And so this is 960. And so that is actually our maximum right here. And this guy is our minimum right here. So our absolute maximum does not happen at 2, but it does happen at -4. Okay, it happens at 4, -4, and we get a value of 960. The minimum is 43/16, and that is a minimum that occurs at 1/4. So again, what made me think of that is the fact that, and you can have absolute maxes and mins only happen at the endpoints. That's possible. But I knew what this graph looked like in my head, so it just didn't feel right. I know a cubic graph does what? It goes down, then it comes up, then it comes back down. So I was expecting to have a minimum in the middle, and that's exactly where it happened. I just can't use my calculator apparently very well. And so you guys have seen me make mistakes in class. Now you've seen me make mistakes on videos, and I'm not going to delete that out. I'm just going to go with it because you guys know how that works. And so here at -4, you've got that value right there, and then at +2 over here at +2, you've got the value of 312. So again, that's the way it works. You've got a worksheet to play with, and if you have any questions, as always, reach out to me. And that's the extreme value theorem, and that's the way you will do every single problem in section 4.1. All right, I'll talk to you later. Thanks.